Okay. Yeah. Hello, everyone. So welcome to the Bangalore Theory Seminar Series. So we are glad to have Professor Anirbit Mukherjee today with us. He's an assistant professor in computer science department at the University of Manchester. His group specializes in the theory of deep learning and scientific ML/AI for science. He's a member of the London Mathematical Society, Alice Society, and the Center for AI Fundamentals. Professor Anirbit did his PhD from Johns Hopkins University and later was a postdoc at University of Pennsylvania, Wharton. Yeah. Over to you, Professor.
Hi, thanks for the introduction, but in the meanwhile, I've lost the window. So let me try to figure out how to get back to my window where the slide was.
Okay.
Do you see the slides?
Yeah, I can see the slide.
Okay, wait a second. How do I get this? I used to see the slides. Okay, when I'm seeing the slides, I don't see anybody's face. Somehow the two are not on my same screen. It has disappeared. How did that happen? Let me just stop sharing once and start reshare again.
I think it is fine if you don't see the faces. We'll stop you if you have question.
Okay. No, I think I figured it out. I think now you can see my screen, right?
Yes.
And you can see the slides. Yeah, I'm pretty bad at tech. Like, tech is pretty bad. Okay, so now the slides are on your screen, right?
Yes.
Okay, cool. Thanks a lot for the invite. I know I've been hearing about Arindam for quite some time, so it's great to be invited by him to IISc. I first came to IISc in class 10, KVPY. So after that, I get back to after a long time. So this talk is going to be about theory of operator learning. That's what we do. The most of the talk will be around this paper in TMLR from last year, size lower bounds for deep operator networks. This was a work with Amurtha Roy, who is a PhD student in IIT Delhi currently. He worked with me, then joined IIT Delhi for his PhD. And towards the end, I will also touch upon this recent work called Noisy PD Training Requires Bigger Pins. This is a work that recently completed with Matthew Colebrook at Cambridge and our joint PhD student, Sebastian Andersloan. Someone saying something?
Sorry, I think the person was not on mute.
Oh, okay, cool. Let me know if you have any questions. Okay, so the other two things we touch upon. So this has been in the news for quite some time now, I believe. Most people would have noticed it, I think, that neural nets can solve PDEs. And this has been going on for last many years. I mean, the earliest papers are from early 90s. But in recent times, thanks to the GPU revolution, this has caught on. People have figured out how to make it actually work at scale. So all big journals you know of probably have covered it in their front page sometime or the other, that neural nets can solve PDEs. And there are many, many ways of doing this. In this talk and for my work, mostly we will focus on what I believe is probably the strongest method out there, which is the operator network formalism. And in particular, I will focus on the DeepONet type of operator nets. There are many kinds of operator nets out there. Each is designed for separate purpose, but pretty much generically it is a deep operator network. So why do we need operator learning? So let me try to motivate the need for operator learning in the following example. So let's consider the simplest nonlinear PDE, what most textbooks start with, which is the Burgers PDE. Del TU plus U del XU equal to kappa del X 2U. The second order nonlinear PDE, the most simple fluid model in some sense. Very simple fluids look like this. And I've put the periodic boundary condition on the fluid flow, and I've chosen some initial conditions. And on the left-hand side column of the slide, you can see examples of the initial condition, which is the blue curve, which is U naught, and the corresponding full solution of the PDE, which is over space and time, which is given in the yellowish green curve, yellowish green surface. So you start with a curve, which is the initial condition, and you get a space-time surface, which is the full solution in X and T. And you can see examples of, I've shown 3 examples on the left-hand side of different initial conditions, each leading to a different full solution. And this is what it means to solve a PDE. So if you think about it, PD solving is about finding this map, which I'm calling the script G. The map from the space of initial conditions to the space of corresponding full solutions. So if you think any PD solving problem is essentially equivalent to finding this operator. All PD solving can be thought of in this language. So the question is, if I want to solve a PD, I want to find this G. Now the question that machine learning people have been asking is, okay, if I have some data, any kind of data about the PD, what is data about a PD can depend on context, but any kind of data if I have, it's necessarily finite dimensional. Can I use finite dimensional, finite number of data to create a machine learning pipeline that will actually approximate this G operator? So notice this G is a map between function spaces. Space of initial conditions is the function space, is the Banach space, infinite dimensional. Space of solutions of the PD is also some Banach space, again infinite dimensional. So this is the map between infinite dimensions. I mean, we are always in infinite dimensions. All of most of machine learning of today is infinite dimensional. So here it's pretty intrinsically infinite dimensional. The target itself is infinite dimensional. Then why should a finite operator, finite machine learning algorithm using finite amount of data be able to approximate this? That is the challenging mystery here. And we understand this in some parts, and we'll get to the details. So this is why we need operator learning. To see real world use cases of this, I'll get to it very soon. Before I get to real world use cases, let me give the most basic architecture that we consider. So the most basic kind of operator network architecture is what you see on the screen, which consists of two neural networks, both having the same number of output nodes, Q. So the red dots are the output gates. So there are Q gates on the branch net. The top one is called the branch net, and there are Q gates in the trunk net, the bottom one. So it makes sense to take inner product of the output of the two nets. And the input to the branch net is called S, I'm denoting by S, and the input to the trunk net is P. So a deep operator net takes two vectors as input and gives you a number as output. That's the most basic operator network. And of course, there's a lot of mathematics out there which I'm not getting into as to why this is generic. In a pretty rigorous sense, one can pretty rigorously say this is a generic operator, but that's outside the scope of today's talk. Almost all neural operators look like this. This can be formalized, but we are not getting into it today. So this is what we focus on today. So let me motivate why this is going to be really useful in far future, let's say. Before I get there, let me introduce a loss function. How would you do machine learning? Most machine learning algorithm, almost all machine learning algorithms need the notion of loss function over the parameters, and which will have to then be minimized. So here, what is the loss function? So let's start with first defining what is data here. So let me consider the setup where I have sample solutions of the PD. So what does a sample solution of the PD look like for me here? It's a 3-tuple. As you can see in the screen, U0 vector is a discretized representation of the initial condition. This could be something as simple as you take the initial condition function and just sample it on some grid. That's your U0 vector. Or you can do much more complicated kind of discretization. Formally, any discretization is the projection from infinite dimensions to finite dimensions. So you can choose any kind of finite dimensional subspace of your infinite dimensional Banach space and project the function down to that Banach space. That's a discretization. So any projection from infinite to finite dimension gives you a way to discretize. The simplest discretization is just sampling it on a grid. That's your vector U0. Z is a space-time location, some space-time location. And UZ is your knowledge of the true solution at x, t. So in this setup, we are assuming that we have some knowledge of the true solution on a sparse grid. Using this, can I set up a loss function? Yes, which is what you see in the red equation down there. So it takes G tilde is my operator net. As I said earlier, it takes two vectors as input. The two vectors it takes as input is U0 discretized and Zi, the location where I know the approximate solution. And we are penalizing the output for not getting the true solution correct at Zi, and then squared loss over it. So it's a squared loss over not getting the true solution right at the different query points Zi corresponding to different initial conditions Ui0. Make sense? So this is a squared loss, simplest squared loss. Of course, there are reasons to believe squared loss is not optimal. That's a separate research we have done. We believe Hubbard loss is better, but we are not getting into that story for now. Squared loss is fine for today's talk. Of course, I should mention that there are technical reasons. We have proofs in separate papers which say where we have established why Hubbard loss is probably better than squared loss. That's a separate research direction, but squared loss for today. So how do you use it actually? The real use cases we imagine that will unfold slowly over time, this is a very futuristic research now, is something like tsunami warning. How does tsunami warning really work? You have buoys floating around in the ocean far away from the coast, and you measure the buoy displacements due to the ocean waves. And by noticing the pattern of the displacement of the buoys very far from the ocean, you can predict that, okay, this is some weird displacements happening, so probably there's a tsunami coming, which will hit us sometime later. But how do you actually find the time of contact with the shore and the tsunami from buoy displacements? You have to solve the water wave equation, the equation of propagation of waves on water, from the data of the buoy displacements far away. But how do you actually solve it? If you get down to the details of how do you propagate wave patterns hitting the shore from buoy displacement, you will realize that this is actually a pretty complicated PDE model that has to be solved. And these PDE models are PDE models. This model is not accurate. Nobody has the exact equation of wave propagation at high velocity and high heights across an ocean. So these are approximate models, still pretty complicated models. And if you run a PDE solver, your solving time might often be greater than the tsunami hitting time. So by the time your code actually gives an answer, you're dead. So this is really a crisis situation can happen if you have strong enough displacements. But such kind of a scenario can be avoided by operator learning. Because what you can do with operator learning is you could have trained the operator previously on historical data of buoy displacements to tsunami hitting time. We have a lot of historical data like this. What was the wave pattern 100 miles away from the ocean before the tsunami hit? This kind of data is available. You could have trained an operator to learn this mapping from buoy displacements to tsunami hitting time and have the operator ready. If the operator is ready, now when you observe new buoy displacement pattern, you can just feed it as input to your operator and out comes the tsunami hitting time. It's instantaneous technically now. So if you have previous historical data about the natural event, you could have pre-trained the operator and an inference just run inference and get instantaneous predictions of calamities. So that's kind of the real use case we are targeting eventually. It's coming up soon, in near future. We are already doing this kind of things in weather. Weather forecasting is already getting there. So this is like where you want operator learning to work. And this is, if you think about it, a map from infinite dimensions to infinite dimensions. Because buoy displacement is a discretization of an infinite dimensional object, which is the wave pattern on the ocean. So that's the promise of operator learning and why we are so keen on pushing this theory ahead and to understand why operator learning is cool. I hope I have motivated this story. So let's see what is the mathematical guarantee about it. So this is the key mathematical guarantee that was recently established. So if you think about it, a DeepONet is basically a DeepONet, which is called script n on my screen, is a map from space of continuous functions on some compact domain D to square integrable functions on a domain. There's L to U. So CD to L to U is a map. You take the function, a continuous function, discretize it, pass it to the operator net, evaluate it on all kinds of trunk inputs, you get a square integrable function. A solution operator is also a map from continuous functions to square integrable functions. Of course, you can relax this square integrability a little bit here and there, but you can also relax the continuity by doing some things, but we are ignoring those fine details. Let's just work with a simple scenario where DeepONet and the solution operator both are maps from continuous functions to square integrable functions. So it makes sense to ask, can I approximate one with the other and when? So the key result, the big breakthrough result, I may say, was established in 2022 by this paper by Lanthaler, Siddharth Mishra, and George Kanadakis, where they were able to show that under pretty general conditions, just barely some measure theoretic integrability is all you need, that for the G, the target operator is such that every function it gives us output is square integrable in the measure that you're looking at. It's a pretty mild condition, actually. Under very mild conditions on the operator, you can always find a neural operator n such that in the L2 norm in the mu measure, it's below epsilon. So this is universal approximation theorem, but in infinite dimensions. Every operator actually is close to a DeepONet. So this theorem existed in some form in early 90s, but the assumptions were very strong. In particular, the original proof in the early 90s worked only on depth 2 nets. It did not have a high depth version. 2022 version is arbitrary nets, arbitrary operators. And now we have a universal approximation theorem for it. Okay, there's a question.
So I have a question. So this is, you're saying it exists, but is there any algorithmic way to find this network as well?
Yes, so the algorithms is the next step of the research. There are many algorithms that seem to work for sure. They're working at scale, but there is no provably correct algorithm. That's the big question.
Okay, thanks.
So this is an existence theorem. And this was in 2022, which in some sense started the modern version of the subject. The earlier versions were depth 2 for much more restrictive operators, but now we have this general theorem. Okay. Let me give some more intuition about how the operator net works. If you think about it, operator net can be written as a sum of products of functions. As I've said above, so beta I in my notation is the ith coordinate of the branch network, and tau I is the ith coordinate of the trunk network. So the inner product can be thought of as basically sum over I equal to 1 to q of beta I evaluated at the branch input times the ith trunk input evaluated at the input xt. So when the two nets are being optimized simultaneously, it's a double optimization problem. You can think of it as essentially finding two things. The trunk function, the q trunk functions that are being defined can be thought of as giving you a set of functions which specify a subspace in the solution space of the PD. So the trunk specifies a subspace where you're looking for the PD solutions. And you can think of the branch net as specifying the coefficients with which to combine the spanning set given by the trunk to get a PDE solution, a candidate PDE solution. So basically in infinite dimensions, you are running a search where you're looking over all possible finite dimensional, all possible at most q dimensional subspaces. And inside them, you're looking for the best possible function. So it's a double optimization that is running. I think this is a very useful view to have of how does a DeepONet work. It searches for the best vector in the best subspace of dimension at most q in infinite dimensions. From this intuition already, you can start to see that q being large should help. That's the point I'm trying to make out of this slide. This way of thinking should already tell you that large q should be helpful. Because large q means you're looking at a larger subspace in the infinite dimensions where you're searching. So you already have an intuition why q being large, that output dimension of the branch and the trunk being large should be helpful for PD solving. But how large is the key question, which I believe is a very fundamental question and quite a hard question to answer. And let's see how far we can go with answering how large should q be. So this is the intuitive version of our key theorem. We say that if you have noisy training data, which is the real world, all data is noisy, then if you look at a set of DeepONets of a fixed size, and you look at all of them have different output dimensions q, and you are training with n data points. So you have n noisy data, and you're looking at the set of all DeepONets of a fixed size. Then you can come up with a threshold of training error such that the only possible way to get the training error below the threshold depends on the noise in the data. So I'm not asking for minimization of the loss. This is a very technical point to understand in this theorem. This is not giving a criteria for minimizing the loss. It says, let me ask for a very simple thing already. Very simple thing. Can the training loss get below the noise in the labels, which is a very mild requirement? And this theorem tells you that just to satisfy even this mild requirement, you already need q to scale with the number of training data as omega n to the power of 1 by 4. So there is this lower bound on the output dimension of which scales with the number of training data. So having large training data does not immediately give you an advantage unless you have proportionate increase in something in the architecture to absorb that information. Yes, question.
So Q is not a function of the threshold. It's only a function of this n, or it's also
It is a function of the, yeah, it is a function of the threshold. Those constants are absorbed in omega. My point is that those dependencies are not important.
Okay.
Yes, all of that is absorbed. There's dependency on the size actually. That's also absorbed inside omega. I'm focusing on the dependence in the number of training data. The point is trying to say is that if you increase the number of training data, you're not guaranteed to get a performance jump. Having more noisy data is not a free lunch. You have to do something to the architecture to absorb that information to get a leverage out of it. And that
but
currently
with the threshold getting smaller, how this Q grows? Is it like if threshold is constant, it's just a constant?
Yeah, this is a constant threshold. So this is a constant noise value. So there's a noise variance sigma. So sigma is absorbed inside omega.
Okay, thanks.
Size is also absorbed inside omega. So Q has to be at least the fourth root of n. So let's see how we prove this kind of things. First of all, some advertisement let me make. There are very few such machine learning theorems. So lower bounds on architecture is a rare type of theorem. So I can almost count on my fingers the 5 papers in all of deep learning where you can get any theorem which looks like this. So I'm very happy with this result for one of the first reasons. It's very hard to get lower bounds on architecture, circuit size. There's basically circuit lower bounds in deep learning. So circuit lower bounds in deep learning is a very rare thing. So there are very few of them. This is one of these. Second is this is universal in the sense that the theorem has no dependency on what PD you are trying to solve. This is a universal lower bound. Of course, one might say that you probably also want to have PD specific lower bounds. You probably want to say that, okay, I want a lower bound which depends on the what PD. Maybe this n to the power of 1/4 is weak lower bound if the PD is, let's say, Navier-Stokes. Possible. And that's currently a very hard open question, which we don't know how to solve. Currently, it's a universal lower bound. But PD specific lower bounds could get higher, and that's a very hard research question that I would like to do. We are gearing up towards that, but not yet. So how do we prove such a thing? Let's start formalizing. So the data is considered to be IISc. Yi is the noisy label, the noisy PD solution, corresponding to Si being the discretized initial condition, Pi being the location parameter. Yi is a bounded finite data. I can assume it's bounded. And branch and trunk net spaces are defined here are Lipschitz functions with bounded weights and whose infinity norm of the output is bounded by some constant C. So this is basically the script C bounding that you see on the infinity norm of the output is basically abstracting out having bounded activation in the last layer. So you could have ReLU activations everywhere in the net. So nothing is bounded inside, but last layer, I need a bounded output. So you could have some proportional to sigmoid gate, something like that, so that it's bounded output. So that's C. Lipschitz functions, and they are weight bounded. Nothing more is required. It's abstracts out the neural net architecture in these 2 lines. Rest of the details of the neural net architecture don't really play a role. Okay. Now, corresponding to the branch net class and the trunk net class, I need to define the DeepONet class, which, as you can see in the first box above, is set of basically all inner products. Take every branch function, every trunk function, you can multiply them to create one DeepONet. So the set of all DeepONets gets defined that way. Corresponding to the DeepONet class, I need to define something called a theta cover space, as I've done below. So this is where slightly things start to get technical about why the proof needs this cover space to be defined. What it basically does is to say that, okay, if you have the weight vectors in the branch space, and you have the weight vectors of the trunk space, you can choose a theta cover of them, which is all weights, choose a set of weights in the branch space such that every branch weight is at most theta by 2 away from your cover points. Similarly in the trunk points. So if you choose these cover spaces for the weight space and the trunk space, you can of course combine them back to get a branch and a trunk, and again inner product them to get a DeepONet. So that's how I'm defining the H theta space. So H theta space is a set of DeepONets which exists by definition by looking at the cover points of the branch and the trunk. So their weights are at most theta by 2 away from every possible weight that is possible for the branch and the trunk. So that's how the H theta is defined. Okay. Next thing I need to define is this concept of Lipschitzness in the weights. So this is slightly not regular thing for deep learning, but it's a very important part of deep learning, but somehow it doesn't occur most often, but it occurs here. Is this concept of this J inequality, which says that given any two weights in the branch for the branch, W1 and W2, look at the supremum over all possible inputs to the branch of the infinity norm of the gap in output between at W1 and W2. And we're assuming that this supremum over all inputs of the distortion in the output of the branch over weights W1, W2 is actually linearly upper bounded by J times W1 minus W2. So this is like Lipschitzness in the two norm versus infinity norm. So any Lipschitz constant of function, you have to choose norms on two sides. So here you can see this is this supremum of infinity norm is the left-hand side norm, and the L2 norm is the right-hand side norm. It's like a cross norm Lipschitz constant. So this cross norm Lipschitz constant is a bit rare in deep learning, but it exists. And we are assuming that constant is J. This Lipschitz property is known to be true for all standard neural networks. So this is not an assumption. This is just provably true for every net, almost every architecture you know of. There are explicit bounds on J available in literature. I would strongly recommend this paper by Universal Law of Robustness via Isoperimetry by Sebastian Wiebeck and Mark Selke. Their paper has a lemma which explicitly gives bounds on J. And this paper strongly influences our work also. So this J is a Lipschitzness in the weights. So this is slightly different from Lipschitzness in inputs, for example, which is a little more common. So this is not Lipschitzness in inputs. So Lipschitzness in weight deviation. Okay, so far with the definitions that we need. Now let's start proving the theorem. So the theorem goes through four main arguments, 4 steps to this proof. Step 1 is not really a step. It's a standard result. I'm just quoting it, nothing of our discovery. So this is a covering number theorem that is you can find in almost any book now. In almost every machine learning book would have it said somewhere. I'm just quoting it for reference. Which says that if I look at the weight space of the branch, I'm just adapting it to my notation basically. So in my notation, what I need is to say it this way. So WB be the weight space of the branch net, WT be the weight space of the trunk net. Then of course, the weight space of the DeepONet is the cross product of the two weight spaces. Now, since I've assumed the weight space is bounded by some WB, and I've also assumed that the weight space of the trunk is bounded by some WT, the non-curly Ws. And dB and dt are the dimensionality of the two spaces. The dimensionality where they're embedded. So dB is the number of branch parameters, dt is the number of trunk parameters. So if I have a compact set in finite dimensions, embedded in finite dimensions, then the theta cover of such a compact set has an upper bound. So what is the size of the covering space of this kind of sets? So these upper bounds are well known, and I've quoted them for branch and the trunk separately. You can see 2WB root dB by theta to the power of dB. And for the trunk, it is 2WT root dt by theta to the power of dt. So these are super exponential in dimension upper bounds. This might look weak, but try improving them. I think it's not easy to improve them. So these are very hard to improve bounds. They're pretty standard bound, but I think these are very hard to improve these bounds. These are super exponential. I think it's under I don't know if there's any natural restriction where you can get it below super exponential in dimension. So these are some standard numbers. Now I use the covering number fact that theta covering number of the DeepONet space is at most the theta by 2 covering number of the branch and the trunk. So you can multiply and get an upper bound on the theta covering number of the weight space of the DeepONet. Okay, questions?
No, I was just curious, like about the broad techniques that you use in proving this lemma. Is it just like, I don't know, analysis, functional analysis, or like what kind of broad techniques people use in proving this lemma?
I would say all of this is basically what people would call high dimensional probability. Verschirin's book.
Okay.
Roman Verschirin's book.
Yeah. We follow that.
Yeah, so all of this is high-dimensional statistics, Martin Wainwright's or Roman Bershine with high-dimensional probability. So this is that.
Thanks.
Or some people might call it geometric function analysis. So these are all geometric function analysis. So this is a standard result about covering number counting, which I've just quoted it for my notation. Okay, now the real work starts from lemma 2. What is the second lemma? This is where the real story starts, the proof story. This is a cover shifting lemma. What this is trying to do is to saying that, okay, let's look at two DeepONets. I've already explained to you the theta cover space, that you have this DeepONet and there exists this, if given any DeepONet, there exists a corresponding theta by 2 shifted DeepONet, which has its branch weight and the trunk weight shifted by at most theta by 2. Now the question I want to ask is, when I do this theta by 2 shifting of the weights of the branch and the trunk, by how much does the training loss change? This is a very important thing to understand. Under weight perturbation, controlled weight perturbation, how much does the training loss change? Unfortunately, there's no general theorem in machine learning which gives me this answer. I think it's a very important result that somebody should try to prove in general machine learning, but we still don't have a general understanding of this kind of things. So we have to do the calculation from scratch step by step again. And it turns out the answer is somewhat interesting. If you think about it, every time I've given this talk, somebody in the audience has asked this question. So this time I'm preempting the question. If you think about how much should the training loss change, if you make an order theta shift in the weights, you might have thought the answer is quadratic in theta, but the answer is linear. And this kind of often I have found that when I've given this talk earlier, somebody in the audience would have always thought that why is it linear? So let me just preempt the question this time. It is not quadratic, it's linear. The reason of this linearity is because of the boundedness. If I did not use bounded branch and trunk net, I would have gotten a quadratic in theta shift in the training loss. Training loss would have increased at most quadratically in the weight perturbation. But it does not increase quadratically. It, fortunately for us, and fortunately why the proof works, the training loss here shifts only linearly in the perturbations. And you can see here in the right hand side, it's linear in theta, and the theta comes with a bunch of constants attached to it. 2cj times b plus 2qc square. Q, you remember, is the branch and the trunk output dimension. C is this critical number, the constant which upper bounds the output of the branch and the trunk. And b is the label size magnitude. So this is a very important part. I don't know of a general theorem in machine learning as to, I believe there should be such a general theorem that under certain general conditions, all training losses probably shift linearly in weight perturbation. This theorem, now that I've proven this theorem for DeepONets, I believe such a theorem is true in general for some class of machine learning. The general theorem is still missing, but here we are. So it's very important to note that the shift in training loss is linear in weight perturbations. And this linearity is because of the boundedness I've assumed. If I did not have boundedness, the whole thing will, this whole thing goes haywire. The whole proof logic goes haywire. And it not only goes haywire, if you have unbounded operators, I think my claim is the proof is going to be extremely hard. Like it's way beyond hard at this point. Even basic ideas will start breaking apart. Okay, this is the cover shifting lemma. Third lemma is where things get more technical. We now start to get to the heart of the matter. So there is this very interesting quantity that I have to now define. This is what is called a noise correlation quantity. So what is noise correlation? I have defined this variable Zi. What is Zi? Zi is yi minus the conditional expectation of the label on the input data. So yi is the true label of the ith data point. Expectation of y given SIPI is the conditional expected label conditioned on the input data. So it makes sense to call Zi as the label noise of the ith data point. So now I hope I have motivated that why Zi makes sense as the noise in the ith data. Given that, I am now looking at this quantity, 1 over n sum over I equal to 1 to n, h of w b theta by 2 t theta by 2, which is the theta by 2 shifted DeepONet, its output evaluated at the ith data point SIPI, this output multiplied by Zi. So if you think about it, I think it's obvious that this 1 over n sum over I equal to 1 to n hzi is the correlation between the DeepONets output at each of the training data and the noise in each of those labels. So this is the correlation between the DeepONet and the noise in the data. And I'm asking, what is the probability that there exists some DeepONet whose noise correlation is at least theta by 4? You can ask why theta by 4 and not theta by 39. It's a proof technique. That number 4 is just helps write the proofs. If you use some other numbers, constants will change, proof gets hard. So there are constants adjusted to make the proof look nice. But the whole point is it is above a certain threshold, which is what gives the meaning that is high. So we are asking, what is the probability that there exists some DeepONet whose correlation to label noise is high? And it turns out this probability is upper boundable. And here is the upper bound. You can see the complicated looking upper bound I've given here. Point to note about the upper bound is that this upper bound, each of the two terms, there are two terms here. First term is super exponential in dimension, it growing up with dimension. And the second one has no dimension dependence. But both the terms are exponentially going down in the number of training data. Both of them have an e to the power of minus n part, which means that right-hand side is exponentially going down with number of training data, which kind of feels intuitive. If you have a lot of training data, it should be hard to find a predictor which correlates to the label noise. I hope that is intuitive. Let me know if it's not. If you increase the amount of training data, it gets harder and harder to find a predictor whose average correlation with the label noise is high, because it has to correlate across so many training data. And here we can mathematically, quantitatively see by how much it gets harder. The probability falls exponentially in the number of training data. And this is where the proof sort of clicks. The proof clicks from here. That you can prove that there is an exponential rate at which number of training data decreases your probability of finding a high noise correlating DeepONet. Okay, so far so good. But but my theorem is about training loss. I want to minimize training loss. I want to get the training loss below label noise. Then why am I looking for noise correlation in the training data? Turns out these two quantities are very closely related. And this is one of my most favorite parts of this research. It's okay. Let me for now maybe skip a little bit the proof technique of how this happens. If people are interested, I can get into the detail of how this proof is done. It's basically some kind of Chernoff-Hövding, but on a very carefully constructed random variable, which has particular right concentrations to get it right. But for now, let me just skip this technicality of how this proof is given. Let me get to the more interesting part, the lemma 4, which tells you what I believe is one of the most very interesting parts of this general insight that has come out of doing this kind of research for me. This is something that people talk about intuitively a lot, I think, but it's very hard to find a theorem that is actually proven quantitatively. That you cannot minimize the training loss unless you correlate to the label noise. The two things have to go hand in hand. There is, unless you correlate to noise, you cannot learn. You cannot do training. Learning is different, but training cannot happen. And this is what this theorem makes quantitative. Look at the left-hand side here. Left-hand side is what is the probability that there exists a DeepONet whose training error over n data points is below sigma square minus theta. Sigma square is the variance in the label noise. Okay, you can define the technical, you can see the technicality of how sigma square is defined in the theorem statement. It's given average of the expectation of the variance of label noise. Basically, you're trying to get the reason why sigma square is defined in this slightly odd way, because I want to make the proof general that this is not IID sampling. I am not assuming IID data. Every data could be separately sampled from a different distribution, it's fine. As long as all of them are finite variances, the average variance is sigma square, that's fine. It's not IID sampling is not necessary for this proof essentially. But that's just a minor technicality. But sigma square is label noise. So left-hand side is basically saying what is the probability that there exists a DeepONet whose training loss is below sigma square minus theta. And it says that this probability of existence of such a good training predictor is upper bounded by some quantity which exponentially falls with the number of training data. Kind of makes sense. If I have large number of training data, it should get hard to minimize the training error. Plus the probability that there exists a DeepONet whose noise correlation is above theta by 4. Which means if you read this inequality the other way, if the probability that there exists a low training error DeepONet is high, it would immediately imply that there is a high probability of there being a DeepONet whose noise correlation is also high. You cannot have one without the other. Low training error is possible. If low training error is possible, you must have somebody who is highly correlated to the label noise. And this is why we have to control the label noise correlation if we want to understand training errors. So now we have 4 parts of the story. Now the job is to put this 4 together. How do you prove? How do you prove lower bounds? How do you prove circuit lower bounds? So this is the, maybe on one might say, the general technique of all circuit lower bounds in some sense. I'm not sure I have the expertise to make that comment, but I feel like saying it, that probably a lot of circuit lower bounds have the same structure, proof structure. What do you want? What we want is this black line, that probability that low error DeepONet exists, this should be above 1 minus delta. I am looking for the necessary condition for this condition to be true. Make sense? So how do I find necessary condition for a certain high probability event to happen? By coming up with a upper bound on that high probability event. Whatever is the good event I'm looking for, let me find an unconditional upper bound on the probability of the good event. If I can find an unconditional upper bound on the probability of good event, then wanting the good event to happen with high probability sets up a tension in the game. And that's how lower bounds come about. So let's start the proof in the cover space, which is where I have most control, h theta. So first step 1 is to invoke the noise correlation to training error transfer lemma in the cover space. I've just written it down, invoked on h theta, lemma 4, invoked on h theta. But this red quantity, which is the probability of existence of some DeepONet whose noise correlation is high, is exactly upper boundable. We just computed it. This was lemma 3. So plug it back. The whole big expression has now plugged it back. So now I have an explicit upper bound by combining lemma 3 and 4 of, so this is this full bound of probability that there exists a DeepONet in the cover space whose training error is below sigma square minus theta. And as you can see, the upper bound, there are 3 terms in the upper bound. Each of them is e to the power of minus n. The whole upper bound is crashing exponentially in amount of training data. Large training data, it gets more and more improbable that you can find somebody with low training error. And voila. This is exactly, the left-hand side is exactly the thing that you are looking for in some sense. Of course, small thing to note, this is still happening in the cover space. But I want to do the final good event must be in the actual DeepONet space. So how do I go back? That's a cover shifting lemma. Go back to lemma 2. So I can take this upper bound on the probability of events, good event happening in the cover space and move it to the real space of DeepONets by doing the shift of the error. I know how much the error shifts between the cover space and the true space. So I do that shift. And then that's the good event. Now I know the upper bound on the probability of the good event in the true DeepONet space. But that's what needs to be above 1 minus delta. So I have a huge inequality. Bunch of messy algebra, couple of pages of messy algebra. Just crank through the algebra and you can get an upper bound. And you can get the lower bound. So formally stated, this is the condition that exactly sigma square minus epsilon into some constant will show up as how much you can get it below sigma square, where the lower bound kicks in. If you want the training error to be sigma square minus epsilon into some constant, then you must have q greater than or equal to c into n to the 1 by 4. So c is this constant that I was hiding in the omega notation earlier. So here is in full glory what c looks like. As you can see, C has a very complicated dependence on a lot of things. It depends on the total weight bound W. It depends on the size of the architectures S in a very complicated way. It has root S to the power of S into e to the power of minus S. It's kind of an exponential log of a certain log of something slightly super exponential kind of a dependency. And it also depends on this alpha prime parameter, which is kind of a ratio of the how much are the weights distributed between the branch and the trunk. Is the branch has more parameters than the trunk, or the trunk has more parameters than the branch? The relative share of the parameters also affects the constant. So there are kind of bunch of subtle dependencies in what the constant is, but I would take the position that this is not that important. The real important thing is independence is completely separate as n to the power 1/4. Of course, you can always read the up bound in the other way and get a size lower bound. You can directly read this as a size lower bound on the DeepONet actually. Just that if you want to write it as a lower bound on S, the expressions are too unclean. It's just not easy to interpret expression, but technically this is the size lower bound on the full architecture also. But we don't state it that way because it's just hard to interpret the theorem constants and all. So I rather read the theorem as at a fixed size, what is the minimum output dimension requirement? It scales to n to the power 1/4. Okay. Now I ask a new question about this. Is this possible to experimentally check the tightness of the lower bound? I have no understanding at this point. I can't prove if this lower bound is tight. I don't have a matching upper bound to argue tightness. It's looking very hard to get matching upper bounds. So can I somehow do an experiment to check, is my lower bound tight? So I started thinking of this, and we came up with a kind of a convoluted way of thinking about it. Let me try to explain what we did. So we look at this PD, which is a very famous PD called the ADR PD, advection diffusion reaction PD. It's a nonlinear PD order 2. We chose a bunch of constants for it, the diffusion constants and the K constants, and we ran the PDs, and we had sample solutions of the PD available. For some reason, I had this available in my setup. And we ran DeepONet training on them. The way we ran the DeepONet training was in a subtly controlled way. You can see two experiments. You can see 20 neural nets or 20 operator nets being trained on this slide. 10 on the left-hand side, 10 on the right-hand side. All of them are training at the same size, nearly the same size. So there are 20 models being trained on your screen. All the 20 models have approximately the same size. It's not fully controlled same size, very hard to do full exact control, but almost all the 20 operators are the same size. But there is one subtle difference between how the left-hand side models are trained and how the right-hand side models are trained. The left-hand side models, when the Q is changing, when the output dimension is changing, I am increasing the amount of training data as Q square. N is going up with Q square. In the right-hand side experiments, N, the number of training data, is not growing as fast with changing output dimension. It is growing as Q to the power 1.5, not Q square. So the right-hand side experiments are slightly data bottlenecked compared to the left-hand side experiments. And you can see that there's a significant, immediately visible difference in how the performance changes. In the right-hand side experiments, you can see that blue curve, the one with the smallest output dimension, is performing the worst, is the top line. And as Q increases, the performance is going monotonically better as I go to the green line. And on the right-hand side, there is barely any order. It's kind of haphazard, the order. There's no clear order. So it seems like I can interpret this diagram as saying that if I increase N, the number of training data, quadratically with the output dimension, then I can get a monotonic improvement in performance. But if I slightly bottleneck the data supply to Q to the power 1/5 instead of square, this nice pattern is distorted. So it clearly shows that a certain amount of data scaling is required to get monotonic performance growth. Now, I would claim that this experiment is kind of interesting. This is kind of a scaling law. That this is the scaling law that machine learning is so much about is scaling laws. So much of machine learning is like the earliest papers in machine learning in 1980s also were talking about scaling laws of this time. It's a very old idea of scaling laws, but getting more and more important these days as we are entering the regime of, as we are entering the modern ML regime where the number of training data is so high compared to model sizes. Like now the ratio of the model size to training data is like, I don't know, 10 to the power -6. You have 1 million data points per training parameter. Almost that's the kind of compressions regimes we are getting into now. But data is so much more than model sizes. So this kind of things are very important, getting more and more important now. And now at this point, let me make a slight leap of faith. My claim is that, or this experiment tells us that since n going as Q square, gave me a monotonic growth, I can probably say that the ideal lower bound is root n and not n to the power of 1 by 4. So I can't say it with full confidence, but I'm kind of betting that my experiment tells me that the true lower bound is quadratic, is square root and not 1 by 4. And there is a scope for improving the theory. I'm not sure. I can't say from my experiment that for sure this theory can be improved beyond 1 by 4. The lower bound can be pushed to root n instead of n4, n by 1 by 4. I'm not fully sure, but I feel that such experiment hints that maybe there is a square root n lower bound, which we are still missing in theory. And even if this theory is tight, proving the scaling law directly is definitely interesting research. So maybe the lower bound theory is tight at n1 by 4, but there is an n going as q square scaling law. Please prove the scaling law. I just don't know how to prove such scaling laws yet. So in either way, this is it. Either you can read it as saying you the lower bound can be improved, maybe, or you can still prove the scaling law. That's an important future question to ask. The second future question that I would like to focus on towards the end of my talk is to say that please note the proof is modular. There are these 4 separate lemmas I had to prove. Of the 4, one is like a covering number inequality, which let's not count it. It's a general theorem of mathematics. The second, third, and the fourth are really the key parts. What was the second part? It was showing that there is this training loss has this particular way of shifting under weight perturbation. Third lemma was about showing that noise correlation has a certain upper bound. And the fourth lemma was about showing that noise correlation and the training loss have a probabilistic relationship. So this is a very modular proof structure. Now, tomorrow you can take any machine learning model you have, ChatGPT, why not, and prove the same 4 lemmas for ChatGPT. Why not? It's not impossible. And for all I know, recently there was a very nice paper by from TIFR, Piyush Srivastava at TIFR. I think Piyush wrote a paper recently where he has almost tried to do something like that. So it's very interesting that Piyush's result and my result almost came out simultaneously. So Piyush at TIFR has written a paper which has very similar story to this thing. So I think all of us are now converging to this idea that maybe this modular proof structure will work for many machine learning models. So I think there's some general machine learning theory we can probably write that this 4-part story can be written for everything. And once you have it, you can get a circuit lower bound. There are general circuit lower bounds possible if you can crank this whole wheel of 4 lemmas. So we went ahead and tried cracking it on another interesting aspect. So the other interesting aspect is physics-informed neural networks, which is another way of solving PDEs by neural nets. It's a very interesting competitor to DeepONets. Pins are one PD at a time. It is not operator learning. You take one PD and you have one neural net solving that PD. So it's a simpler question in that sense, but it's actually harder machine learning because the training objective is so much more complicated than operator learning. So the advantage between pins and operators is, I would think, a very interesting question to think about. I have some views on where is which one more helpful, but fine. So we went ahead and looked at pins. With pins, we looked at the PD, which is the Hamilton-Jacobi-Bellman PD. Why Hamilton-Jacobi-Bellman PD? Because it has a lot of cool properties. A, it is scalar PD. B, it is easily writable at D variables. Any dimension scalar PD, it has the same form, very nice to look at. It has exact solution families available at every dimension. A lot of easy testing is possible. And it's a very nonlinear PD. So nonlinear PD, easily definable at all dimensions, kind of looks like a nice test case to start with. So we went ahead and did a pin experiment on Hamilton-Jacobi-Bellman PDs. And the experimental data we get is this. I believe it's a very cool experiment, this graph that we could produce. What you see on the screen is y-axis is the accuracy of performance, 1 minus the training error, final training error. We are calling that accuracy. And every blue line is one neural net that has been trained. Dn is the size of the neural net. Number of parameters in the neural net is Dn. So that blue dots are basically logging the value of the accuracy every 100 iterations of training. And red point is where the algorithm converged. So every blue line is one training of one DeepONet of that size. So you can see that the accuracy is increasing as Dn is increasing. Kind of makes sense. It's a log scale graph. So the accuracy growth is square root in the size of the neural net. But after some time, the accuracy saturates. So there is this threshold effect. All of this is happening at a finite amount of data, noisy supervision data. So once I've fixed the finite noisy supervision data, there is this threshold effect that eventually, after some time, all nets are going to perform nearly the same, no matter how much size you have. We believe this is very generic, that this is kind of a generic effect of machine learning, and it's not easy to establish how often you get this shoulder effect. But here we are, a very controlled setup where you can see the shoulder effect. That beyond a certain size, performance does not increase anymore. It's just almost plateaus out. So can you explain this? Theoretically, we can explain such a thresholding effect. Is there a critical neural net size? So there seems to be a critical neural net size. Can you theoretically pick that out? Answer is almost yes. Same proof strategy as we have. Take the same 4 lemmas, prove it again for the Hamilton-Jacobi-Bellman PD solving a neural network. Sorry, neural network solving the Hamilton-Jacobi-Bellman PD. Run the same analysis again of these 4 lemmas. Now the calculation is 5 times more complicated than what I showed in the earlier part of the talk. Because as I said, the pin loss function is so much more complicated because the full differential operator is part of the loss function. So you have to do a perturbation analysis of the differential operator. And this is a nonlinear differential operator in d dimensions. So how do you do a perturbation analysis of a nonlinear differential operator in d dimensions? It just gets algebra is super messy. So you have to do 10 times, 5 times more algebra, but it works out. The whole of algebra works out. The whole same 4 lemmas can be proven again with much more complicated constants, much more complicated factors involved, blah, blah, blah. But it kind of same proof strategy will work out. And it will give you a lower bound. But now the lower bound is the total number of parameters, not just on the output dimensions. In this, because of the way the pin loss is structured, we can actually get a lower bound on the full parameters. So here it is, the red line. Dn is the neural net size. Dn log dn must be greater than equal to ns eta square. Eta is the amount of by which you're pressing down below sigma square. And ns is the number of training data, noisy training data. And it says that here is a lower bound. It's an actual circuit lower bound. Now this is like a true blue circuit lower bound of how many parameters do you need dn, which is scaling with ns. So dn log dn is approximately subquadratic in dn. So dn is subquadratic in dn above ns. So this is like, if you take it the other way, dn is like mildly sub-square root ns. So this is like so there's a circuit size lower bound which is sub-square root the number of training data. So dn is upper bounded by ns to the power of half minus epsilon. You can read it that way kind of. So here is a circuit lower bound, which is HJB specific. This whole analysis for the Hamilton-Jacobi-Bellman PD. So this tells you that there is a critical DN where training loss minimization starts. So, and somehow experimentally, we do see that this critical size is kind of approximately does match where the thresholding started in this graph. So we are very excited about this result. Next step is this HJB specific? I don't think so. Currently, the entire analysis for Hamilton-Jacobi-Bellman PD, but maybe neural nets have this particular circuit lower bound for many more PDs. I am very optimistic that this is not HJB specific. Neither is this experiment HJB specific. I don't think it is HJB specific, but that's the research we are doing now. We are trying to reproduce this data for other PDs and trying to see. And I have a very strong feeling this lower bound is also not HJB specific, because if you look at the proof very carefully, there is a one particular lemma inside it which actually is PDE dependent. And I have a feeling that lemma is probably true for many PDs. And there are many PDs where this sub-square root lower bound is true. And that's the research that we're trying now. That's the end of the talk. Sorry, I went over some time, I believe. Please ask me questions if you have any.
Thank you, Professor. So, one trivial question. So, like in the architecture, so the evaluation points of the output that we are getting, so are that fixed? Like, if I understand correctly, so the points where the outputs are getting evaluated. So is that like
you mean the trunknet inputs?
Yeah, like not need to like look back at the terminology again. but like the
This one,
evaluations that we are doing for the output functions.
ZI.
Yeah. So are those like fixed in advance, or like our network can give it like any number? Like the numbers of the evaluations are fixed, or the where we are doing the evaluations are fixed?
Yeah, the theory doesn't assume anything about them being fixed anyway. Like you can, in theory, it doesn't really care at this point about how you choose how you sample uh, the function space, how you sample the evaluation points. None of this matters to the theory at this point. You can choose any way of sampling the points for any way of sampling the functions. Theory is currently pretty blind to all these choices. But
Yeah.
you can
So my
ask, experimentally, does it matter? Can be your question. If you say experimentally, yes. Experimentally, a lot of these choices matter. How you sample the function space is a big effect. How you choose this discretization grid for the solutions. So it's experimentally, these choices make a big difference. Is that your question?
Yeah, part of it. And like the other part was like once my network is trained, so let's like on that test data, so I'm given a like input function. So the output function that I'm getting is like the samples of that. So I will be getting like the samples of the output function, if I'm correct.
Not really.
Okay.
After the training is done, you get a function. The function is it's a function defined on the entire domain, which is a surrogate PD solution on the entire domain. The
Okay.
DeepONets are very powerful in that way. That is one of the reasons why I love DeepONets. That's why I love proving the theorems about DeepONets. DeepONets are super powerful from that point of view. After the training is done, it's a full function. Like there's nothing discrete about it anymore.
Okay.
After the training is done, any valid domain point is a valid input to the trunk net.
Okay.
You take any point in your domain, put it as input to the trunk. The answer is an approximate PD solution at that point. So post-training, it's a full function. There's nothing discrete about it anymore. It's a full function, which is a true surrogate of the PDE solution. This is why DeepONets are, I think, very powerful. They promise to give a full function. There's nothing discrete after training. How do you discretize this point? How do you choose the U0 I's, the Z I's to train? That's a discretization choice. So that you can write a training loss and do the training. After the training is done, it's a full surrogate.
Yeah, like it seems kind of interesting. So yeah, we can take the next question.
Yes.
Thank you for the talk. My question is, when I look at the loss function,
Yeah.
I mean, it seems that it does not take into account the regularity of the solutions, the regularity of the original solution and the regularity of the surrogate solution. Is that not
Yes.
important in the context of PDs?
Totally important. Okay, good question. So the issue with the regularity is this. Okay, two parts to that. Let me give the answer two parts. Since this is a data-driven mechanism, it actually should not take the regularity into account, because tomorrow I want to use it for something like, as I said, the mapping from the buoy positions in the ocean to tsunami hitting time. This is the abstractly stated operator which I want to solve for. This abstract operator takes as input the position of the buoys in the Indian Ocean around Bay of Bengal, and the output is the hitting time of the tsunami in Chennai. This abstract operator exists in principle. It's defined through data. So, and I want this mechanism to work there. So this DeepONet loss can be implemented on this data and trained, and you can find an answer. So in that sense, it is good that the smoothness and all this information is not required for the loss and the algorithm to be well defined. Because otherwise, if you had to ask for this data to get the algorithm to be defined, then you would have to know what is the smoothness of the map from buoy positions in Bay of Bengal to tsunami hitting time in Chennai. Who knows what the Sobolev constant of this thing is?
Right.
So I would never be able to use this algorithm if I had to know this kind of information. So in that way, it is good that this loss function does not ask for such information. It just asks for input-output pairs of your observation. But if you know that the operator you're solving for has certain regularity assumptions, like maybe you're solving for a very controlled situation, like Navier-Stokes on a torus with smooth enough initial conditions where solutions are known to exist. The classical Navier-Stokes, where all-time solutions are existing kind of things. There we have a lot of information available about the target operator. Now, when you have a lot of information available on the target operator, you can utilize that to write a better proof of approximation. Like these kind of approximation proofs that I showed here, the classic 2022 result. These theorems can be now improved by leveraging information about the target operator, if you have that. That is possible. I know, for example, please look at the recent paper by my friend Jakob Zeck and his student Niklas Reinhardt. So Niklas and Jakob Zeck, and I think there's a third author, I'm forgetting who the third author is. So Jakob Zeck is a friend of mine. Jakob and his student Niklas Reinhardt have recently written proofs like that, where they have estimated the operator network size in terms of the smoothness coefficients of the target operator. And you can show, they've got a generalization bounds actually. They've got a generalization bounds which are proportional to the smoothness coefficients of the target operator. So if you have that extra information, you can leverage it to get better guarantees. But the algorithm should not be using that information, because if the algorithm started using such information, then the utility of the method will go down. Am I making sense?
Yes.
Cool.
Thank you.
Please look up Jakob and Steinhardt's paper. There you can see an example of how to use smoothness to get better bounds.
Sure. Thank you.
Questions anymore?
Yeah. Okay. If there are no other questions, so let's thank the speaker. Thank you.
Cool.
Thank you.
Nice to meet you all.
Bye.
See you.